Not going to lie, this question's a little bit confusing when you first read it, so I'm just going to restate the question in my own terms. So given that the time-independent portion of the wave function is a solution to the time-independent Schrodinger equation, and also its complex conjugate is a solution, then a linear combination of the two is also a solution of the time-independent Schrodinger equation. So if we take some arbitrary wave function, which I'm just not going to write the x anymore, we should know that's the spatial portion. If we have some arbitrary wave function, we'll call it psi sub 3, is a linear combination of these two solutions to the wave function, then the linear combination of the two is also a solution. So I'm going to go ahead and write the time-independent Schrodinger equation here. We got a double derivative, some potential, and that equals to the energy. Right, so if we go ahead and substitute this psi in, or the linear combination of the psi in, we should get psi sub 3 out on the other side. So let's go ahead and do that. Here's our linear combination. Okay, so as you can see, these are constants, so they just distribute themselves into the parentheses. And since that is a linear operator, that is also going to distribute itself in. So I'll go ahead and do that algebra, but rewrite it in a more suggestive way to save us some time. Oh boy. Right, it's a little crunched on the side, but this is all psi 2 on this side. So we know that this looks really similar to this side, so that's just going to be the energy times, that's just the energy times C1 psi 1. And then this side is the same thing. It's just the energy C2 psi 2, right? So let's go ahead and rewrite that. And again, we'll pull out the energy here. See where we're going. This is all equal to psi 3. As we have up here. It's our linear combination. Okay, so we just showed that these two solutions, linear combination of the two with any arbitrary constant out front, is also a solution to the time-independent Schrodinger equation, which means that any linear combination of solutions, let's say these two right here, are also solutions to the time-independent Schrodinger equation. So let me go ahead and write in orange here. The textbook suggests some linear combinations such as this one, with this one being the complex conjugate. So this is a linear combination of two solutions of the wave function. That was part of the given information, that this is a solution, this is a solution. And so we have a linear combination of the two, and it looks like the two constants that he suggests are actually equal to 1. That is a solution to the wave function. And additionally, this is actually real, because if you think about this in terms of, let's say like a plus I, b, some just like general form of the wave function, and its complex conjugate would actually just be bi. If you add those together, that would be 2a, right? So that's real. right? So that's the whole part of the question that he was asked. That he said was show that the solution to the time-independent wave function can always be considered to be real because it can be expressed as a linear combination of other solutions that are real and complex. And another one they ask is this one here. What is it? Yeah. Right, which again is just a weird way of expressing. Let me do it in green. Weird way of just saying, let's say A plus IB. Just this general form of a wave function. Sorry, this is actually the complex conjugate. Right, so that's just I times negative 2b, which then is equal to just 2 times the complex portion, which is, there's no I, so it's real. Yeah, so it's kind of a weird question in my opinion, but the whole point is, given that these two are solutions, show that any solution to the time-independent wave function, when in a linear combination, is also a solution as well. And then you can just show that these suggestive solutions are also, these suggestive linear combinations are also a solution to the wave function. Yeah, weird question.